For every piece of treasure, we create a special kind of lock. A lock that needs one key to close it and a different one to open it. Two different keys, two different processes. The first key, the locking key, we make available to everyone. A public key. Second one, we make impossible to replicate. They're linked by a mathematical function, an algorithm using prime numbers. Public key cryptography.
Okay, so let's P be a prime number. Prime number 2, 3, 5, etc. But in practice, we're gonna make sure that it's a big prime number, like really big, and you'll see why. So if you give me a prime number, I can create this set called ZXP. The X is for all the integers up to p minus 1, excluding 0. So 1, 2, 3, up to p minus 1. So let G be a primitive root mod P. For example, suppose P is 23 and let's say G equal 5. If I ask you, do you think 5 is a primitive root mod 23? You're gonna have to maybe find the cyclic group of 5 and the order, that is the number of elements in this cyclic group. And last time we said we had an algorithm for computing the order, right? We didn't want to have to find all these powers and then up to 1. To answer the question if 5 is a primitive root mod P, you can simply compute 5 to the power what? We have the integers 1, 2, 3 up to 22.
Yeah.
And what are the factors of 22?
So that would be 1, 2, and 4.
No, 11.
Not 4, huh? Okay, 1, 2, and 11, and 22. Okay.
And 22. And you remember, so because we have to take 5 to the power 1, 5 to the power 2, we have to try all of them. And last time you made a very, very interesting observation, is that if you want to find if it's a primitive root, why do you have to waste your time to all this? Why don't you just check this one, right?
Yeah, exactly.
So if 5 to the power 22 mod P mod 23 is 1 mod 23, then we can say that 5 is a primitive root mod 23. So the idea is for any P and G, if you do G to the power P minus 1, P equal 23, P minus 1 is 22, mod P, if that gives you 1, you don't have to try the factors of P minus 1, you just take P minus 1, you raise G to the power P minus 1, if you get 1, that means G is a primitive root mod P. Does it make sense?
Yeah.
Okay, why is this important? Let's say you have two persons, let's call them A, like Alice, and B, like Bob. Alice, it's a female. Let's make her a female so people don't accuse me of being a... exchange a message between you and your friend. What is the message? For example, you want to send her, or she want to send you the number 4. It's like, okay, I want to send Oman the number 4, and Oman want to be able to tell Alice, listen, you sent me the number 4. This is the secret message that you two want to be able to exchange. Here's the problem. Let's say this is the internet. Would you agree with me, Oman, that the internet is not a secure line of communication?
Yeah.
Like people who are trying to crack your credit card code and everything, you send an email through a channel which is not secure. What is the Diffie algorithm? How does this use prime numbers and primitive root in order to send information without having to worry that someone might crack the information. So I'll give you the step. Step 1. You two, or the two persons that are trying to exchange the message, have to agree on two numbers. So you agree on a number P, which is a prime number, and like I said, it has to be a very big number. So like 23 is way too small. Also have to agree on G. G has to be a primitive root of P. So if you do 5 to the power 22, now since 22 is even, you can write 5 to the power 2 times 5 to the power 2. So I'm trying to get powers of 2. So what is 5 to the power 2 mod 23? 5 to the power 2 is 25. Mod 23 is 2, right?
Yeah.
What is 5 to the power 4? So now you have to do 2 times 2, which is 4, right?
Yeah. 4. That's true.
And now if I want to get 5 to the power 8,
16.
it's 16. And if you do 5 to the power 16, so it's going to be 16 times, do you have your calculator?
Yeah, so like 16 times 16, which is 296, and that would give us
Mod 23.
That would be 3.
3. Now I want to reach 22. So now I have to multiply 5 to the power 16 times 5 to the power 4 to get 20. 5 to the power 4 is 4. 3 times 4 is 12.
And 5 to the power 2?
5 to the power 2, which is 2. 2 times 2 is 24. Mod 23 is 1.
Mm-hmm.
So I kind of wasted your time, but I wanted to do this exercise so that in the exam question, you can't just say G equal whatever number is a primitive root. You have to show him your work, right?
Yeah.
Okay, so we do know that this is prime and this is a primitive root mod 23. The question that I want you to ask him is this number unique? Probably not. Maybe 2 is also a primitive root. You can try this later, but ask him if 2 is always the case. If you have the question like this, the algorithm says you have to start by choosing the primitive root. You can just the choice. Look at this. Step 1, Alice and Bob will have to agree upon a prime number and G, which is a primitive root. A primitive root, not the primitive root, right? This is a public information. They also call public keys. It means that this information can be available on the channel, the unsecure channel of communication. Like for example, you can pick this from the internet. Everybody can know these numbers, and you guys don't have to worry about that. You'll see why in a moment. So we have public information as long as P is prime and G is a primitive root. Step 2, and this is the most important part. A has to choose a secret number. B has to choose a secret number. For A, I'm going to call it small a, and then for B, small b. Let's say, for example, A equals 7. So this person choose 7, and then B choose 10. They are secret.
Yeah.
If you provide this information to on the public space, then that's really bad. The algorithm is not going to work. Now you're going to tell me, but Oliver, can't anyone like try to crack these numbers? If P is a very large prime number, it's going to be almost impossible for people to find what's the value of A and what's the value of P. So like if anyone is sitting here trying to crack the message that I'm trying to send you or trying to send me, the person will have to guess what is the number that this person chose and what is the number that this person chose. If you don't know these two numbers, there's no way, for all practical purpose, there's no way, or it's going to be extremely difficult. It's going to take you years to try to find out what is the message that they're trying to exchange. Okay, so that's the idea. So step 2, they don't have to be prime, by the way. 10 is an even number, right?
Yeah.
Okay, but they have to be secret. And then step 3, we have to compute. So this is what A has to compute. So each party has to compute a number. A is going to compute the number G to the power whatever that number A is mod P. So in this case, this person is going to compute G is 5 to the power, which number did she select? She selected 7. And then mod the prime number, which is publicly available. And what is 5 to the power 7? Okay, we didn't compute this, but I'm just going to give you the answer that he gave so I don't waste your time. I think you know how to find this number, right?
Yeah.
You can do 5 squared, 5 squared, 5 squared, and then 5.
Yeah, and we know like 5 squared is like 2. So
It's
that'll
2.
be 2 times 5. So like 8 times 5, right?
So how much is this?
So if it's 8 times 5, that would give us 40 minus 23 minus 23. Is it 17?
It's 17.
Okay.
That number 17 is what this person A, after computing the number 17, is going to send to B. Now remember, this number 4 is the actual message that you want to send me, and or I want to send you, but we don't want people to see this because these hackers are going to use it and maybe do something bad with it. Instead of that, you send me, see, A computes this number and send it to B. People can see the number 17. It doesn't matter because the real message is 4. What do you think B is going to compute and send to A?
So would it be like G to the power of B?
Perfect. So B compute, what is G? Is 5 to the power 10 mod 23. Now, you already got 5 to the power 7, which is 17. Can you use
And
that to find 5 to the power 10?
I remember 5 to the power of 8 was 16.
Okay.
And 5 to the power of 2 was 2. So 16 times 2 is 32. So that would mean like 32 minus 23. Was it 9?
It's 9. So B is going to compute 9. And what does he do with that? He says, I'm going to send it to A. Here's the interesting thing. This is an unsecure line of communication. This person sent 17 to B. B sent 9 to A. These information are public or can be hacked, but it's fine. And the numbers P and G are also public. P equal 23 and then G equal 5. So you have those 5 numbers are public. The only thing that is hidden is 7 here, and this is 10. And the message is 4, which is supposed to be. So now you might say, how do I know that B is sending me the message 4? Because the only thing I receive is 9 and B is receiving 17. So let's see how A and B are going to decode the number 4. Okay. You have a secret number which is 7, and you have a secret number which is 10, and the public information is 23, G equal 5, and this is what you sent me. So can you take a guess? It's okay if you don't know, but what do you think A will do after receiving this number to try to determine exactly what is B trying to tell me? I know it's not 9, it's something which the claim is it's 4, but how would she know?
So like there's something here that gives us 4.
Yes, but you don't even know that it's 4, right?
Yeah. So like, is it, for example? No, I don't think so. No. I was gonna say like, is it like 17 minus 9 divided by 2? But no, right?
It would be too easy.
Yeah, right?
Hackers will think it would be too easy. So here's the secret message. For A, is going to take that number 9, and then you raise it to your key.
Okay.
And then you do mod 23.
But we did this last time, right?
No.
We didn't do 5 to the power of 7?
But we sent it to B.
Oh, yeah,
B did something else because B used his own key to compute the power he sent it to us. Now we're going to do something. We're using the number of B to raise it to our key again. Actually, can we do this? And You see, because if what you're claiming is true, this should give us the some numbers that we already found before, right? Can you quickly try to find 9 to the power 7? You can like do the powers. 9 squared is 81, or
so like so like 9 times 9 would be 81, and like minus 23 minus 23, that would give us 12. So 12 times 12 times 12, that's 9 to the power of 6 times 9. That would be 6 times 12, that would give us 9 to the power of 6. And that would be 3. So 3 times 9, right?
27.
And so that would give us 4.
They give us 4. And that number 4 is a new number. And so, but what you're saying is interesting, because you're right, in a sense, isn't that what we did before? The problem is A did 5 to the power 7 and then send it to B, and B did something else. He did 5 to the power 10. I don't have your number, you don't have my number, right?
Yeah.
And yet, without even knowing your number, I am able to decode your message. The actual message that Roman wanted to send me is the number 4. And let's say I want to double check. So you send me 4. I'm like, hey, I want to tell Roman that I actually received 4. So what is B gonna do with the number 17?
Will it be to the power of 10? Like 17?
17, perfect. 17 to the power 10. And now that's a big number, so you have to trust your professor. This command is equal to 4 more 23.
Okay, so so with that we made sure it was 4 and we got it, right?
Exactly.
So I have a question. So let's say a hacker knows the number of PNG, which is fine, it's public, but they also know that the secret message is the number 4. Could they get like the A and B?
No. So they don't want. Okay, I thought. Here's what you have to say. Let's say they know P and G, which is public, but they also know 17 and 9, which is also public. What is the most important information in this? Is it 17, 9, or is it 4?
No, it's 79, of course, because it gives 4, right?
Okay, no. So, I mean, what is the thing that A and B are trying to tell to each other?
Okay. In that sense, 4 is important. Yeah.
4 is important. So your question is, if I know A, B, P, and G, can I crack the number 4? That should be the question.
Yeah,
right?
That's true. But like what I meant is like, obviously, they want 4, right? Like if they got 4, then they shouldn't try.
They shouldn't
but let's
try.
Say, let's say they have P and G and 4, and like they feel like they're very good. Could they get A and B?
Yes, exactly. Yes, but it's gonna be way too easy. Now let me tell you. So let's say a hacker want to find A and B from what?
From A and B.
And G and P.
P.
Because all of these are public. It says it's known as the discrete log problem. This is computationally what?
Difficult problem.
Difficult. The reason why it's extremely difficult is because of the fact that nobody knows how to factorize prime number, especially when they're really huge. So if I give you 23, you might say, okay, Oliver, 23 is 1 times 23, right?
Yeah.
Okay, according to ChatGPT, this is a prime number, okay? When you look at this number, can you even guess? And you might say, okay, but Oliver, you can use a calculator or something. Trust me, if it's prime, it's extremely difficult to factorize. Now you can use a calculator, you can use an algorithm, you can use a computer program, but it will take you time. And it gets even crazier as you use longer digits. A bank, for example, my bank is CIBC. When I try to log in on the internet to access my bank information, you have like a code, I think it's more than 12 or 13 or something. You have like characters A, B, C, D, but even each letter is actually converted into digits. So these are really, really big numbers. So because you're dealing with a big prime, the claim that your professor is making here, that this is very difficult to compute. Yes.
Yeah, but that's a good thing, right? Because that means it's safe.
Oh, exactly. It's secure. And the reason why this algorithm become very popular is because nowadays almost everything is done over the internet. You buy your books, emails, like checking e-transfers. Can you imagine if this wasn't safe?
Yeah, that would be a big problem.
It would be terrible.
Yeah.
So it's very interesting. I think one of the most interesting application of this course, operation like mod, primitive root that apparently have nothing to do with anything in real life are actually used to encode secure communication between two parties. It has real life application.
That's true. Yeah, but I have one question.
Yes.
So like you said that what makes it hard is because like the prime number is very big, right? Like
Yes.
it's a big number.
Yeah.
But like as you know, like with improvement in AI like can do the calculations for us. So do you think like that could be a way? I know it's still a very big number, but couldn't AI like take the time to do all kinds of factorizations of that number?
Yeah. So if I give you a very, very, very big prime number, can you factorize it easily? You see the answer?
Okay.
No. If you give me a very, I cannot factor because prime numbers by definition have only two factors. That means factorization blah blah blah. However, if you give me a very large composite number, factoring it in prime, that's why cryptographic systems like RSA rely on difficulty of prime for what?
For security. Yeah.
So here's what you can do. You say, okay, Oliver, I'm gonna hire a team of hackers with a lot of computers, because if anyone can do it, that means our communication on the internet is not as secure as we thought, right? If someone claimed the price, people are gonna try to find other ways of better algorithm and things like that. So there's a value into offering money to hackers. Nobody, and they are very smart mathematicians in the world, they don't know how to do it. If you want to do 5 to the power 2 mod 23, you do exponential 5, 7, 23, it will give you the numbers, you know?
Yeah.
It's like, is this number prime? True, it's prime. And it's gonna use Lagrange algorithm, do the factorization, and then boom, do all the calculation, and then at the end find the message. So
World War II. The German wolf pack prowled the Atlantic. Their orders sent in code. The codes were unlocked by this. Enigma, a kind of key. Every submarine commander had one. Inevitably, during the sea battles, one fell into enemy hands and the cipher was broken. Key sharing led to the fall of the Nazis. So, how do we deal with this problem in the Silicon Age? How do we keep our precious keys safe while still making them readily available? Answer. For every piece of treasure, we create a special kind of lock. A lock that needs one key to close it and a different one to open it. Two different keys, two different processes. The first key, the locking key, we make available to everyone. A public key. Second one, we make impossible to replicate. They're linked by a mathematical function, an algorithm using prime numbers. Public key cryptography.